Now you should remember from an earlier video that I did that the cardinality of a set, let's call that set A, and let's say that it's a set and it has a certain number of elements in it, and we've got the cardinality, which is the number of elements of that set, and that's just the number of elements. Okay, so what happens when we have infinitely many elements? What happens when this cardinality is infinite? Well, you might say that cardinality is infinity, and that's great. So let's have a look at something that does have infinite cardinality. Let's say the natural numbers, which is the set that starts like 1, 2, 3, and so on, so all the positive integers, and we say that the cardinality of n is infinite. We can have a look at a different type of set. We can say, I don't know, 2n, and what do I mean by 2n? Well, I mean every element in n multiplied by 2. So that's just 2, 4, 6, and so on, and that is in fact the set of all even positive integers. And this has cardinality infinity as well. But you might be thinking that since 2, 4, 6, and so on are all integers, then 2n is actually a subset of n, because every element in 2n is also in n, so it becomes a subset. Great, but you might also think, hang on, they both have infinitely many elements, so you might think that they should be the same set. However, we know that they are not the same set. Why? Because, well, okay, have a look at 1. 1 isn't in 2n. We've found an element in n that's not in 2n. So you can say that 2n is a strict subset of n. But they've both got infinitely many elements. So how can one be less than the other? How can one be smaller than the other? Well, that's what I'm about to talk about next. One of the most fundamental rules in set theory, and specifically in the cardinality of sets, is that if we have a 1-to-1 correspondence, so 1-to-1 correspondence between sets, so between, say, two sets A and B, then, well, if we have 1-to-1 correspondence between two sets, that means we can match up every element in one with an element in the other, and we can do this for every element in both sets. Then the cardinality of one is equal to the cardinality of the other. More generally, if you can find, so if there exists a function, apologies for my handwriting, if there exists a function from A to B, so you take the elements in a set A and you map them, we say you map the elements from the set A to B, that is 1-to-1, then the cardinality of A is less than or equal to the cardinality of B. And what this does is it says that, okay, we can map from A to B, and that gives us a less than or equal to, and then if we can also map from B to A, that gives us B is less than or equal to A, so it follows that you get this result here. Okay? We've defined the set 2n to be the set of all even integers, where we've multiplied the elements of n by 2, all of them. which means that we can have some function, which I'll call f, that goes from a to b with this notation, and for x in n, f of x equals 2x. And what this means is that our function takes elements from n, or from a, so I should probably write a, and it multiplies them by 2. That's all it does. So we've found a function f, so you take, say, 1, 2, I don't know, 17, 18, and so on, and they map to 2, 4, 34, 36, and so on. So we've found a mapping from A to B. Okay, great. We can do the same. We can say that G from B to A, well, what is this? So we've got the elements of 2n, which are 2, 4, 6, and so on. We can divide them by 2 to get back to n. So for x in B, we can say that g of x is a half x. Great, we found a mapping from A to B and a mapping from B to A, which means that the cardinality of A is the cardinality of B. So just rewrite A and B. The cardinality of n equals the cardinality of 2n, despite them both being infinite. But we say that they have the same cardinality.